Hi there and welcome back. Now that we are done with the static concepts, we can now move on to our next topic, which is the fundamentals of stresses and strains. Okay, so this topic is something like an overview of what the strains and what the stresses are all about. And of course, recall that these stresses and strains are just simply a result or obtained from internal loadings, um, which is also a result of I mean from the external loadings and support reactions. Okay, so to start, it must be understood that in the study of mechanics, we assume that the body is a continuum. So that means that, for example, if I have an I-beam right here, okay, and no matter how small or no matter how many times I divide this material, I don't get into the right. I don't get into the atomic structure of this steel I-beam. So for steel, the composition is iron plus carbon. That's the primary composition, and also plus some other alloying elements. But this is the main composition. It's an iron and a carbon. Okay, so going back, when we say continuum, no matter how many times I divide this steel, I don't get into this atomic structure. Okay, so just you, I mean, if you compare this continuum to the quantum assumption or the atomic view of matter, wherein for atomic view of matter, when you divide it, you get into some point wherein it is no longer divisible. So that's what you call atoms, indivisible. But for continuum, it is infinitely divisible. But when we analyze it, there must be some point or some elements wherein we can take for analysis. Okay, so that element is what we call infinitesimal element. Okay, so that's why in our lecture handouts you see that this I-beam, there's actually a grid, because it's the representation. I mean, if we just take one, okay, so it will look something like this. Now the question is it always a cube? Of course not. That depends upon the coordinate system, but most common is the rectangular coordinate system. So that's why it's like this. Okay, so we take that cube and we analyze what's going on in there. Like for example, if I subject this beam with external loads, then um, I made a section cut, and then I would want to analyze this infinitesimal element and then check the loadings. Okay, so somehow if I know the loading of this infinitesimal element, then if I integrate this, so somehow I can get the overall loadings in the, or I mean stresses or deformations in the entire body. Okay, so that's the concept of continuums, and many times we will be dealing with this infinitesimal element. Okay, and by the way, about the integration that I said or that I mentioned, it just makes sense if you have a non-regular shape. But for regular shapes, like for example I-beams or circular shapes or rectangular shapes, then sometimes you don't need the integrations. Okay, anyway, another important concept is that the concept of the rigid body. And when we say rigid body, if we have this body right here, right, and I made a a grid, and this grid is in terms of the points. Okay, so you would notice right here that there's gonna be a distance, right? This distance between the points. So we have this distance, we also have this distance, and we have this angle right here. So when I apply the load, when I subject this body into external forces, and this one deforms, let's say it changes to something like like this because of the external forces, or it can change to something like this. Okay, so you would notice here that there's a change, right? There's a change in the length of the distance between these two points. Okay, so another one is when we subject a loads, and this one is specifically shear loads. And if we notice a change in the angle, right here is 90 degrees, but right here it's no longer 90 degrees. Then there's a change in the angles, or there's a change in the length. That's what we call a deformable body. Okay, now let's talk about the history, or some actually brief history of the strength of materials. And although there are many individuals who made large contributions in the development of the strength of material subjects or solid mechanics, I would like also, I would just mention only three of them. Okay, and I just would like to highlight the experiments, or the or their conclusions on that particular experiments that they made. Okay, so first one is Marriott, or Edme Marriott. This is around 1620 to 1684. Okay, so his experiments is he did experiments on the strength of the beams and then the strength of actually loaded bars. Okay, although Galileo also did experiments on the strength of the beam, but they arrive into a different conclusions. Okay, and I just would like to highlight here that one of his experiment is to load this, let's say this bar in tension. Okay, so when he loaded this bar in tension, he noticed that if you increase the load, right? So first this is the load, and there's gonna be a deformation, and then if you increase furthermore, then also there's gonna be a deformation. Of course, it will elongate, but then there will come into a point wherein this bar will break or fracture. Okay, so I describe his experiments as something like about the fracture, the fracture of materials. Okay, it's not yet the fracture mechanics. I mean the rigorous fracture of fracture mechanics. This is just the fracture because it breaks apart. Okay, so that's one of his experiments. So meaning that in this date, I mean in this timeline, they were already doing experiments on the strength of materials, and they noticed already that when you apply a load on a material, then at some point or at some load value, this material will break. Okay, so they noticed that already. And by the way, this timeline is around, or probably just a little before the timeline of Newton. Newton around 1600s or 1700s. Okay, so that's it. That's the Marriott experiments. Now another one is Robert Hooke. Now, Robert Hooke is also a contemporary of Newton, although I think he's before Newton. Before, just years, just some years before Newton. Okay, so Robert Hooke. This is 1635 to 1703, and he had an experiment on the springs. So the setup is that here's the spring, and he noticed that once he applied the load, okay, so once he applied a load on the spring, this spring elongates. Let's say this is the load, and then if we increase the load, he noticed that there's also an increase in the deformation. Okay, so right here is the initial position of the spring without the load, or let's say that's the original shape. And once you apply a load, then it it elongates right here, but for this one it elongates this much. Okay, and he concluded that the amount of force to restore this material to its original position would be just simply related to the deformation right here. So that's his conclusion. His conclusion is that the amount of force, he called it restoring force, the amount of force for a material to for a deformed material to return back to its original position is just simply related to the deformation. Okay, and it is oftenly expressed as F is directly proportional to the deformation. So the amount of force, this force, the load from this, or the force from these loads. So that's the weight. So it is expressed as the force is directly proportional to the deformation. And if we take the constant, proportionality constant, it becomes F is equal to K times the deformation. So this one is the force, this one is the deformation, but with regard to this experiment, this is just a linear deformation, and this K value is what we call the stiffness. So that means that if a material has a higher stiffness, it means it requires more force to be able to deform. Okay, so if it has a lower stiffness, then even just with a small amount of force, then you can just deform it easily. Okay, but the concept of returning back, I mean of loading and unloading and returning back to its original position, this is the concept of elasticity. So when we say elasticity, it's a property of the material wherein you can or the ability of the material to be able to go back to its original shape once it is unloaded. Okay, so from this unloaded portion, if I remove this, then if it can go back to its original position, that's what we call elasticity. Okay, and then another one is Kaoshi. Okay, Kaoshi, the timeline of Kaoshi is 1789 to 1857. So this is actually after Newton, because he's also the one who introduced the concept of limits in the calculus. Okay, but in the strength of materials, his contribution, or one of his contribution is the concept of stress. So probably because of his mathematical background, he's more into, or is more inclined towards the mathematics. Probably because of that he was able to arrive into a rigorous analysis of the strength of materials, and this is the concept of stress. And although based on my readings that this concept of stress was just somehow similar to the concept of pressure at a point in fluid mechanics. So in fluid mechanics, if we have this, let's say a body of fluids, and we take an infinitesimal element. So right here, this is one of the application of the of using the infinitesimal element for analysis. Okay, so if we have static fluids, all right, so meaning that static means that there's no motion. If there's no motion in the fluids, then all the forces that's acting on these infinitesimal elements are just normal force, meaning forces that are perpendicular to the area of concern. Okay, so this is from fluid mechanics. It's only perpendicular forces, but for strength of materials, he proposed that it's not only the normal force, but also there must be some forces that are parallel to the section area concerned. Okay, so right here we have two forces that are parallel, and these are In terms of stresses, by the way, stress is just simply the force all over area. So in terms of stresses, this is what he called shear stress. Okay, so shear stress are stresses that are parallel, I mean where the force is parallel to the area. And this one, the normal force, which is similar to this one, this is what we call this is what he called the normal stress, or sigma, in terms of sigma. This one is in terms of tau, this is sigma. Okay, so because of this contribution, then it becomes, I mean, the strength of material becomes rigorous, and it actually paved way to more developments. Okay, so now let's talk about the different types of loadings. Now, how do we determine the strength of materials? Because they were already doing experiments way back in the 1600s or 1700s, 1800s. How do we determine the strength of materials? That depends upon the types of loadings. So right here, I mean, right now we'll discuss the different types of loadings. Now, if you can refer to our lecture handouts, so here is our illustration for the different types of loadings. We have here the undeformed geometry. So you see here, there's no forces acting on the material, and if this is the undeformed geometry, this will be the basis of comparison. So when we apply a loading that's axial, when we say axial loading, it's a loading that is perpendicular to the cross-sectional area right here. Okay, so if this is axial loadings, you would notice right here that the grid lines, it actually elongates. And in this particular type of loadings, or in this particular type of axial loadings, this is what we call a tension loadings. And if it is the other way around, that's what we call compressions. If this one produces elongations of the material, this one produces shortening of the grid lines. Okay, so this is axial loadings. Now, another type of loading is the shear loadings, meaning that the force is parallel to the cross-sectional area. So this is our original, or this is our undeformed geometry. So because of this force, downward force, then there's actually changes in terms of the angle. Okay, so right here, this is the undeformed. This one, because of the presence of this force, this becomes the geometry, and this is the deformed geometry. So in terms of angular, although you can relate angular to the length. Okay, so that's one type of loadings, and another type is bending loadings. So bending loadings, they are produced by concentrated moments. Right here, we'll just write, so they are produced by moments or end or flexural loads. When you say flexural loads, these are loads that are perpendicular to the longitudinal axis. So this is our beam right here, and this is the loadings. Okay, so these loadings are referred to as flexural loadings, flexure or bending. And when we apply that, then the deformed geometry will be something like this in terms of rotation. And another one is the torsion. So torsion is also, as I have always said, that this torsion loadings is actually a moment, except that the axis of rotation is along the longitudinal section. I mean longitudinal axis. Okay, so right here I have this mini material right here. So when we say axial loadings, it can be compression. So you will notice here, if I compress this, the distances between the grid lines, they are actually shortenings, or they shortens, or if in tension, then they elongates. Okay, and for bending, okay, so for bending, the loadings would be flexure. So right here, so it will be something like this. So you can have also bending in this direction. So that depends, that depends upon the direction of the loadings, if we consider three-dimensional loadings, right? But when we say torsion, it's the loading in this direction, right? So it's twisting. Okay, so that's torsion. All right, now let's move on to the different tests, because we now already understood the different types of loadings. Then, in order to determine the strength of materials, uh, that we need to classify the strength of material in terms of what? In terms of what loading? Is it in terms of tensile test, or is it in terms of compression test, or is it in bending flexure test or torsional test? So that depends actually, right? And some materials actually they have the, let's say, they have more strength in compression rather than in tension. Example of that are brittle materials such as concrete and probably ceramic materials. Okay, so they have more strength in compression rather than in tension. And for ductile materials, they are more strong, or they have the same or approximately the same strength as when you load them in tension or you load them in compression. Okay, anyway, let's now discuss the different types of test. And this test, by the way, is um, this test is now commonly obtained using a universal testing machine or any testing machine. Okay, universal testing machine. And when you say universal testing machine, it just simply means that you can do, let's say, axial loads, or you can do um, probably bending test or many other tests, okay, for that testing machine. Okay, so the first one is the tensile test. Okay, so from the word itself, tensile, that is axial loadings. So this is the equipment, for example, or the machine, and we have this grip right here and another grip. So this grip is just something like a holder. Okay, and we have this material fixed in here, being held by this grip, and then it is being pulled apart. Okay, so because of the applied force, there's gonna be some breaking point. Okay, and it is translated also to the, or to a plot called the stress strain curve. Right, stress strain curve. Okay, so different materials will have a different stress strain curves. So one example is the steel. So it has this stress strain curve diagram, and it records, if here is the strain, along the horizontal axis, and here is the stress along the vertical axis. So when you apply loads, you apply the loads, you increase the loads, then there'll come a point that there's it's no longer gonna be linear, because right here we have a linear proportion, right? So from this point, from the starting value to this point, is what we call the elastic region. Okay, so if you still increase the load, then the relationship between the stress and the strain is no longer linear. Okay, and this is what we call as the plastic region. Plastic region. Okay, and it will reach some maximum value of load, and this point right here, this is what we call the ultimate strength, actually ultimate tensile strength. This one is what we call the yield point. Yield means that it's about to, or something like it's about to not become linear anymore. Okay, so if this is our yield strength, so we have this yield point, or in terms of strength, let's just say yield strength. Okay, and we have this ultimate strength, and finally the material breaks apart. So this is what we call fracture. And there's actually a lot of things going on, like if you read the strength of material text, there are also necking and other things like that. But I don't want to focus on those things for now, because the most commonly that I've encountered in the computations is this yield strength and this ultimate tensile strength. And also for some materials, there are still other points right here. There are other 2 points, like the upper limit, the lower limit, or the elastic limit, or the proportional limits. A lot of terms, and this is not present in all materials. So it just simply means when you see the point elastic limits, it just simply means that that's the uh, that's that's the point where the elastic region ends, or after that point the relationship between the stress and the strain is no longer, um, I mean, after that point, um, it cannot go back to its original shape, because that's what elasticity means. Okay, so I just included here the yield strength and the ultimate strength. Okay, and by the way, what's the difference between the strength and the stress? Okay, so what's the difference between the strength and the stress? Now, the stress is the loadings, or the external loadings, or the internal loadings, and things like that. But this one is something like the capacity of the materials. Okay, so this is the capacity of the materials, and this one is the from the load side, loadings. This one is the property of the material. Okay, so another question is that you would notice that right here, this is the stress strain diagram, but the original, um, or the more direct, is that it will be the force and the deformation diagram. Okay, so this force and deformation diagram is not the same as the stress and strain diagram, because force has different units than the stress. Now, the problem with this force and deformation diagram is that, for example, if I have this, let's say this geometry, okay, and let's say we have a steel as a material, or as a steel for our test specimen. Now, if I change the geometry, let's say I change this, we have this diameter and we have this length, right? So we have the diameter, we have the length. Now, if I change the diameter twice, if I change the diameter twice, now it will change. I mean, the graph will change to something like this, maybe. And if I change the length twice but retain the diameter dimensions, so probably I would get something like this. Okay, so that means that this force and deformation diagrams changes with the different geometries of the materials. So if you change the diameter or you change the length, then you get a different curve for the same material. Okay, so because of that, we divide the force. We divide this force by the area. So we divide this force by the area, and that's what we call stress. And we divide the deformation by the original length. Okay, and that's what we call strain. Okay, so that's why no matter what's the size, what's the diameter or the length of the test specimen, it will produce the same curve. Okay, so for steel, for example, that's the curve. Okay, another one is that for it's not always this curve. I mean, for other materials like rubber for example. So for rubber, probably the stress strain curve would be something like this. Okay, and for aluminum and steel, many other materials, they will have different types of curves, and sometimes some materials don't have these plastic regions, like for example the brittle materials, so they don't have that much plastic regions, they just fracture right here. Okay, so something like this, they fracture right here. Okay, so I guess we'll continue our discussion in the next video.